All right, how's it going, everybody? We are here on Friday, March 26th. We're going to be looking beginning of week 10 here. We're going to check out section 8.3. This week in general is a really cool week right here. We're going to get some applications to physics and engineering stuff today in section 8.3. In our next video, in section 8.5, we're going to see probability, which in my opinion is aside from the fact that calculus was originally invented specifically to handle doing physics problems, and in my personal experience, probability has been one of the coolest realms of application of calculus that I've personally experienced. So I'm really excited for section 8.5 as well for our second video here. So today what we're going to look at is we're going to look at the idea of what is a moment. It's a physics word, moment there, has nothing to do with time, as well as center of mass. If we're given an irregularly shaped object, can we determine where the center of its mass is, where a balancing point would be, if we're looking at sort of like a 2D object or perhaps a 3D object that has equivalent thickness here. This is also something that you're probably going to end up looking more at in a three-dimensional setting rather than a two-dimensional setting once you're in a Calculus 50C, right, our third calculus class. As it's been with this whole dang semester, every time we want to talk about something, right, we've seen our integration techniques. Those aren't really necessarily anything that we develop. Well, okay, we've got geometric intuition for most of our techniques as well, but for lots of our applications right here, we've been seeing that it's simple to look at some geometric examples and then for us to sort of upgrade our geometric examples to being our sort of our continuous function examples that we can handle things other than just rectangles, triangles, circles, stuff like that. So today, what our progression is going to be here is we're going to start by looking at the simplest possible case, one dimension, a finite number of objects, right? Then we'll look at two dimensions. We'll see it's not going to be that big of a step up, but we're going to see it. This one's really, really important for us to discuss before we get on to our 2D continuous. This third perspective is really sort of like the actual calculus behind what we're doing here today. Two dimensions and having a function, a border defined by some continuous function of a solid object right there. Again, trying to define a moment so that we can identify its center of mass. So these are kind of the three ideas that we'll talk about here today. And again, the calculus all lives in the third one right here, but it turns out that we're going to need discrete ideas not only to build the formula for the calculus formula, but as well to combine our results from multi-part problems for the calculus scenarios right here as well. So this will be really important. So let's do our first perspective here, the 1D discrete scenario. So when we say one dimension, it means that we only have like an x-axis, there's no y-axis. Discrete meaning we're not talking about the center of mass of like some irregularly shaped object. We're talking about just two objects, right? A discrete number of objects right here. So we have two weights and we're going to balance them on a beam. Object A weighs 10 kilograms. It's placed 8 centimeters to the left of the fulcrum being the balancing point. And then we have this other object B. It's going to weigh only half as much, only 5 kilograms. And so the question is, since it weighs half as much, where should it be placed on the balance beam so that the beam is balanced rather than tipping from one side to the other? Fortunately for us, like several thousand years ago, like 5,000 or 6,000 years ago, a really smart dude named Archimedes kind of figured this out, and he figured this out empirically. He did lots of like actual physical experiments, timed them, weighed lots of things. So Archimedes was an awesome scientist that he didn't do the math to derive the formulas. He did the experiments to arrive at what the formulas must be experimentally. And he's kind of famous for lots of things like this in lots of different realms of physics. So he was a physics nerd before it was cool to be a physics nerd. Back thousands of years before we had calculus, stuff like that, figuring out a bunch of physics concepts here. So what did Archimedes come up with? Well, Archimedes' law of the lever is going to say to us, given two masses, we'll call them M sub A and M sub B, and two distances from a fulcrum. We'll call that distance A and distance B. Those are distances from the fulcrum to object A and object B. Then the beam is balanced. If the mass of A times the distance that A is from the fulcrum is equal to the mass of B times the distance that B is from the fulcrum. So we can use this basic idea right here to go ahead and determine exactly where this should be located. So in our scenario right here, the mass of A is 10 kilograms. The distance that A is from the fulcrum is 8 centimeters. Our mass of B is 5 kilograms. And so what distance should B from the fulcrum right here? Well, this is pretty easy right here. It looks like I'm just going to divide both sides by 5, and that's going to leave me with a 2 right there. It looks like 16 centimeters should be our distance that B is going to be from the fulcrum right there. So really, really easy for us to use this Archimedes law of the lever concept right here. And the reason why this formula is important is this small formula that we're looking at right here is because this is going to allow us to derive a general formula for center of mass. So let's draw a little bit of a picture here, and let's then do this in general. Our next step is going to be to find the general formula for the 1D center of mass of two objects. It's really saying, given two objects on a balance beam, where would the fulcrum need to be located for the balance beam to be balanced here. So just to draw our little balance beam right here, we've got our fulcrum right there, right? So this is our balance beam. It's sitting on this little triangle, this balancing point right here. And what we're thinking to ourselves is that in our situation right here, we had that mass A was this heavy one, and mass B was the lighter one. What we ended up seeing in this case right here is that mass A located at X, or excuse me, I want to call this X of A. It's the location. This was given as being 8 units away from the fulcrum. What we just determined was that mass B, located at location XB, would therefore have to be 16 units away for this balance beam to end up being balanced right here. What we want to do is we want to identify some general formulas for D sub A and D sub B, and also identify what, give a name to this location right here. So I'm going to call this location right here X bar. This is our center of mass in this scenario right here. It's exactly where the centers of those two masses are, given that the mass isn't equal for both of them. So one is further away. That's helping balance out the fact that it weighs less. It's twice as far away from the center of mass because it has half the mass as the other object right here. So that's what we're going to call X bar right there. And we're also going to see here, we're going to define some quantities. I want to know, how do we define in general distance from the fulcrum to A and distance from the fulcrum to B? The one tiny thing about this is really easy. This is just a subtraction, but just remember, we want to think about distance as being this positive quantity. So right here, what I'm thinking is that this is our distance A from the fulcrum to mass A. So I'm going to do what I always do for measuring a distance, is get my final minus my initial. My final location would be the X bar here, minus the initial, which would be X sub A. Alternatively, over here, it's just a subtraction, but notice if I'm finding the distance between the fulcrum and the mass B, then this is going to be the final location, XB minus X bar right there. So just to get two positive distances, notice that those subtractions happen in switched orders right there, so that they're both positive quantities. So the question now is, can we come up with a general way to solve for where X bar should be located if we were given this information differently? Notice in this one right here, we're told what the distance, we're told distance A, distance B right here, but what we're probably typically more interested in is saying, given some solid object, can we determine where X bar would be located? Where is the center of mass going to be given these two objects and their placements here? So we kind of want to solve for a different variable tied to the three general equations that you see on the screen right now. We've got our law of the lever. We've got our two formulas for the distances to A and B. Let's combine all three of those equations to solve for X bar. That'll give us our center of mass between those two objects right there. So we've got our pieces of information here. And again, I'm going to use all three. Maybe I should just kind of indicate all three things that I'm using here. I'm going to use these two, as well as this guy right here is the stuff that's going down there. Right? Mark that off in blue right there. So these three equations we're combining with the goal of solve for X bar. So let's go ahead and do that. We've got that our mass of object A times the distance that object A is from the fulcrum equals the mass of object B times the distance that object B is from the fulcrum. What I'm going to do is replace dA and dB with the two equations that we just stated right here, and we're going to go ahead and solve for X bar. Nothing too crazy right here. So mass of A times X bar minus X of A equals mass of B times X of B minus X bar. I'm going to expand. Oops, XA equals mass b, xb minus mass b, x bar. My goal is to solve for x bar here. So here's the algebra steps I'm going to do. And this is just some algebra, so I'm going to kind of do one quick step here. I'm going to take this x bar term and add it over to this side to get it to group up with the other x bar term. I can see that I'm going to get how much x bar am I going to have? I'm going to have the mass of A plus the mass of B of it because that's a negative, so it'll be positive when we subtract it over here. So I think I'm going to get here x bar times mass of A plus mass of B on the left. I'm going to take this term that doesn't have an x bar in it and add it over to the other side. So you're going to see that we're going to get the sum of the mass times the location for both A and B on the right. And just a quick division is going to give me the center of mass in a 1D discrete scenario here. You should notice that this is consistent enough with the subscripts here that it seems like there's some shorthand that we could use to express this idea right here. It looks like it's just the sum of the ith mass times the ith mass's position divided by just the sum of the masses right there, right? So that's going to be our general formula. You should notice that this is going to, in general, apply to any number of masses. It could be that there's more than two masses if we want the whole thing to be balanced. If we could find that where that x bar would be located given those masses in those positions, that we can go ahead and add up all of the masses times their distances divided by the sum of the masses right here. So we're going to define these quantities right here. The moment of the system about the origin, because it's in 1D, we just say that it's about the origin right here. Well, that's the thing that we're seeing up here in the numerator right here. When we define what a moment is, it's this numerator term of the center of mass. It is the sum of the masses times their associated distances. So m sub I, x sub I right there. And in general, we're seeing that our center of mass that we're calling x bar is really, to say it in words, is the moment about the origin divided by the total mass. And that's, as we just stated, is our m sub I, x sub I, the sum of all those divided by the sum of the m sub i's right there. So these are kind of our two key definitions that we've got here for ourselves here today. Bold right there. So we're going to need to be using these guys a good chunk here to find some good center of mass terms. Now again, this is obviously our simplest scenario, 1D discrete. And we did our example up top sort of there with that law of the lever right there. Nothing too exciting. So let's kind of expand this a little bit into the 2D discrete scenario. This is really just going to be some more repetition of what we saw before. There's just two variables of it. I do want to point out though that there's one very small notational thing that's very easy to get wrong in this that feels a little backwards. When we talk about a moment about an axis, what we're saying here, I guess the thing for you to recognize is that when we talk about the things like distances from the y-axis, stop and think about this for a second. How do you measure distance from the y-axis? It's an x measurement. And how do you measure distances from the x-axis? It's a y measurement right here. So there is a little bit of like x and y stuff that feels a little bit backwards here, but it's only backwards sort of in name, and the math kind of follows the variables that I would think that it would right here. So let's go ahead and identify some of these guys here. Our moment about the x-axis and our moment about the y-axis, notice that our moment about the x-axis, since we're measuring distances from the x-axis, are actually y measurements right here, right? So this is our sum of each of the masses times their distance from the x-axis, a y measurement. And very similarly here, our moment about the y-axis, those are x distances here, so we're going to add up our masses times those x distances that we are away from the y-axis. So just a little bit of like, it just feels a little bit wrong, like our variable subscripts there, but remember, since we're talking about measurements from the x-axis, those are y values. Measurements from the y-axis are x values right there. So when you say it out loud, it makes sense. It just looks wrong when we write it on paper right here. And again, when we do all of our math, our x stuff is going to go with our x stuff, our y stuff is going to go with our y stuff. That's just sort of a notational bit of unfortunate confusion that's technically correct right there. So what can we do here? We can easily find our centers of mass then, that our x center of mass should be our moment about the y-axis, because that's going to be all of our x measurements right there, divided by our sum of the m sub I. And that right there is just going to be exactly what you expected this to be. The sum of the masses times the x distances divided by the sum of the masses. And similarly for y bar, So again, don't worry too much about the kind of swapped subscript of what you're anticipating right there. When we go to do the math, these are all going to be exactly what you expect. See that y bar deals with the y stuff, x bar deals with the x stuff mathematically. Um, so just a little bit of slightly confusing notation is all. So these are our two equations to get center of mass in a 2D discrete scenario right here, right? And again, this is going to both provide us the geometric intuition that we need to get our continuous scenario, the actual calculus setup. And this is also going to then be used to combine the results that we're going to get out of the calculus setup. So this, even though we're not doing the calculus yet, this actually is helping us in more than one way doing the calculus, really. So let's go ahead and do our one problem that doesn't involve calculus here, then set up our calculus formulas and do our calculus example here. So our example is, let's go ahead and find the center of mass of the following 3 point masses. When I say a point mass, this is sort of a physics reference right here. We're saying, don't think of this as being some like weird shaped object, right? Like if I've got my can of Diet Coke right here, not a regularly shaped object, we know that, and especially since I've already drank some of this Diet Coke right here, its center of mass is probably a little bit lower in the can, but probably through the center of the can. This isn't a point mass. The mass is distributed in some region around some central point. Um, I'm just saying, we're not talking about some like weird shaped object. Just imagine a single point that has some mass and space right there so that we can say the mass is located here. We've got 3 different objects. They each have a weight. They each have a location. And what I want to know is where would be the center of mass if we were to do, rather than just a balancing beam, if we were to do like a balancing plate, right? Like put a plate on a single resting point right there. Where would we need to put the point that the balance is located at so that that plate, the two-dimensional plate, would then go ahead and be balanced right there. So the things that I'm seeing right here, a couple things. Mass of A is 2. Mass of B is 4. Mass of C is 12. And that's going to tell me that the sum of the masses, it looks like, is 16 plus 2 is 18. And I can kind of picture what my scenario looks like here as well. I'm just going to keep on writing some stuff right here. I hate having to actually look back up at the paragraph to find my information, so I'm kind of writing this down in my simplest sort of setup right here, all the information I'm actually going to need. And what I'm picturing for myself out here, let's kind of draw this diagram. I think this is kind of important right here. Let's see, my biggest x value goes up to 6. I think I'm just going to mark this as like 10 and 10, so we get a square grid right here. There's my 5 and my 5. And so our points are located at 2, 1, so there's A, 6, 2, so there's B, and 4, 10, so there's C right there. So again, the question is, picture these being 3 weights that are placed on a circular plate. If we were to try and balance that plate on a single point, where would that point need to be so that this is balanced? And notice that not only are these not necessarily like distributed symmetrically here, like C is, the distance from A to C is much bigger than the distance from A to B. B is also like 1 point shifted up from where A is. And most importantly, these all weigh different amounts, right? C weighs double what A and B weigh combined, right? So we're going to need to put the center of mass much closer to C than it would appear that we need to. It's not just the central location, but the center of mass, right? So I'm kind of picturing for myself that my guess would be something up here like much, much closer to C. Also, what I'm kind of trying to do is I like jiggle my pen around right here, and I think you can see it in this. I'm trying to put this dot a little bit more to the right of C than rather than being centered, because I know that object B weighs double what object A weighs, so it should be a little bit to the right of where C is located. It's going to get a little bit more pull from B. So this is sort of my like guess location right there. And it looks like what I'm guessing is like something near, maybe like a little bit bigger than 4, and like, I don't know, maybe something like 7. I'll just say like 4 point something and 7. All right, that's like my vague guess as to where we're going to end up with our center of mass right there. And again, remember that the mass has an impact on this. This isn't the center location. This isn't the average location. The mass is giving us extra pull. This is a weighted average really right here. So let's go ahead and do the math right here then. To find x bar, well, we just came up with a formula for this. It should just be the sum of the masses times their x locations divided by the sum of the masses. And so up top, we're going to get the sum of all three terms. There's three different masses, so we're going to get three different m times x terms right there. The first object, A, weighs 2, and its x location is 2. The second one weighs 4, and its x location is 6. The third weighs 12, its x location is 4. We're dividing this by the sum of the masses. I already computed that because I knew I was going to use it in both formulas, and it's just a quick sum, so there's 18. And if we add this guy up, what are we going to get right here? 4 plus 24 plus 48 over 18. We're going to get a 76 over 18. And I threw this into my calculator right before I did this right here, and I got a 4.22 repeating there, right? And hey, I feel pretty dang good about that. That just making my eyeball and graphical guess right there. It was a little bit bigger than 4, just like I anticipated right there. Let's do the exact same thing for y bar here. So it's exact, nothing different here. We're just grabbing y locations instead of x locations here. So 2 times 1 plus 4 times 2 plus 12 times 10. And so again, notice this 12 units of mass times that location of 10. Notice that this is by far making the biggest contribution out of the three, which is moving our center of mass more towards point C than it was near point A and point B. It's getting that, a lot more drag is going in that direction right there. All divided by our 18. So what are we getting? 2 plus 8 plus 120. Way more contribution from the C term for the center of mass than from the other two. So it's really pulling it in that direction. 130 over 18. Again, I already checked this guy out in my calculator right here, and I was landing at 7.22. And man, I feel really good about the guess that we just came up with up there. Just kind of by a visual estimate and thinking about which one of these is going to have more pull than the other one. I was, accurate to within a quarter for each of those right there just by eyeballing this. Obviously, I've already done this problem, but I think that you guys would have made this exact guess right here. So it looks like we found our center of mass to be located at x bar comma y bar equal to about 4.22, 7.22 if I'm going to round that guy to 2 decimal places right there. Right? So not that bad. And again, this problem right here just did 2 things for us. One, this is going to be what we're going to mimic to produce our integral formula that's going to help us find center of mass of irregular objects that are defined by some boundary function. This is also going to be the way that we are going to assemble our multi-part solutions that we're going to see for the example that we're about to do right now. So now let's do the calculus. And this paragraph right here is just giving you the little don't just discard our little bit of just basic addition and multiplication up there. It's still practical to us for 2 reasons coming up right here. So that wasn't just let's set it up with some easy problems. There's a little bit more than that. This actually will be practical stuff that we're going to do here in a minute, right? And my kind of statement here is many center of mass scenarios involve sort of like piecewise defined regions where the example that we're going to do is a square with a semicircle stuck onto it. So we're going to deal with the square separately from the semicircle, find each of their individual center of masses, then find the collective center of mass by doing some of this math up here, right? So the 2D continuous scenario. So we have a continuous 2-dimensional surface, and we would like to find its center of mass. In this case, what we should think about is that surface really being an infinite number of points that are all infinitely close together, and that we could, in a sense, add up the mass of that one individual atom of our disk and multiply by the mass of that atom and add them all up and divide by all the masses, right? Well, we're just talking essentially about adding up an infinite number of objects. That should be an integral to us. So we should be thinking Riemann type thoughts in this case, in this scenario right here. So let's think about some Riemann sticks. So here's our goal. What we want to do is we want to take, some curve. Here's our f of x curve out there. We're going to go, from A to B as usual right here, right? And what we want to end up finding is where is this center of mass? My goal is to know where is this x bar, y bar. In this case, should be probably ballpark close to the middle right there. Whatever. The goal is to find where that one dot is going to be. And so what I'm thinking that we can do right here is let's do the same thing we always do in calculus. Okay? Here's our f of x. Here's our a. Here's our b. Let's do the same thing we always do, and let's think Riemann sticks. If I'm going to estimate where that center of mass is, I could decompose our region into n Riemann sticks. Since our formula above, we kept on using, well, we had three objects in our last formula, so that doesn't seem like, I'm just going to make this last one over here big. Okay, those should all be of equal width if we're following our Riemann sum formulas right here. But the point is, what I think I could do is I could decompose this into, n Riemann sticks. I could find the center of mass individually of every one of these Riemann sticks. And then, having found the center of mass of each of those Riemann sticks, I can think of each of these rectangles as just a point mass located at its center of mass. I could then use my formula up here to add up all the masses of each Riemann stick times the location of center of mass. That's going to be my x sub I, y sub I in that case right there of that Riemann stick. And that's going to give us our overall center of mass. In this case, just an estimate because we have n Riemann rectangles. We obviously want to let n go to infinity and get our exact location, right? So in this case right here, by the way, a dot is the center of mass of one Riemann stick. Oh, and by the way, important word right here that I'm going to use in a second. Center of mass, or centroid, of one Riemann stick. So again, the process here could be compute the center of mass of each Riemann stick individually, then find the center of mass of all those center of masses of the individuals. This is sort of my idea of like a piecewise process here. You do it for each of the individual geometric objects that make up the overall object, then you find the center of mass of all of those objects right there. And essentially, this is just a weighted average, right? So, so what we want to identify is, let's kind of go through the process of what we need to calculate to be able to do this right here. So we want to be coming up with the centroid of the ith Riemann stick. So my question is, in general, where would you say the location is of each of these dots, or one generic dot? Right? So I'm going to kind of redraw my picture, but just throw in one Riemann rectangle right there. Right? So the question is, where is this centroid, this dot, going to be located, right? So I'm thinking to myself, I'm going to call this location x sub I. If that's the case, then our next x value is x sub I plus 1. And what I'm interested in is not x sub I or x sub I plus 1, but what is always going to be halfway between them. It's a rectangle, so it should just be the average of x sub I and x sub I plus 1. So I'm going to draw a little arrow with this guy right here. This should be my x bar sub I. It's the center of mass of the ith Riemann stick, which is why it's got the bar and the subscript of I. And where is it? It should be at the average of x sub I and x sub I plus 1 over 2. That's going to be the location of the x value of the center of mass of this thing. Now, where's the y value going to be located? Well, the two values that I can see that are relevant to me right here is that it looks like this is going to be f of x sub I bar. And therefore, since this is a rectangle, this is also always going to be, just like this was half the distance between x sub I and x sub I plus 1, this height is going to be half the distance between 0 and f of x sub I bar right there. So it's just going to be half of f of x sub I bar. X bar sub I, I wonder if it matters what order I say those things. So in any event, this should be telling us that where are we located here? Well, that dot is located at x bar sub I, comma, 1/2 of f of x bar sub I, right? The height, but only half the height because we're only going halfway up the rectangle. Really easy to find the center of mass of a rectangle. Really hard to find the center of mass of weird irregular objects. It's why we like rectangles so much. Their areas are easy, centers are easy, widths and heights are easy, all these things. It's why we do so much Riemann stuff. So from this centroid, let's go ahead and determine what our mass should be of the ith Riemann stick. So I'm thinking to myself, again, I'm going to draw our same diagram right here. And I'm going to draw my same Riemann rectangle, put the little dot in it, and just drawing our Riemann rectangle out here a little bit bigger so I can mark some things and stop writing as tiny as possible out here. There's my Riemann rectangle right there, my generic one. What I know about my Riemann rectangles is that we always define them to have a width of delta x, and that our height for these guys is always going to be our total f of x sub I bar, right? It's the total thing right there. So what I'm thinking to myself here is that mass, I know that I can compute mass by multiplying density. I'm going to write density instead of the letter for density first here. Density times area in 2 dimensions. Density, we just use that Greek letter rho, R-H-O, rho, and there's our density right there, times the area. Well, my area is just delta x times f of x sub I bar, right? Delta x times f of x bar sub I, right there. So it looks like this is a reasonable formula for m sub I, right? The mass of our ith Riemann stick right there. Density rho times delta x times f of x sub I bar. That's our area right there. Using this mass, I can now compute the moment of each individual stick. That's the numerator of our overall center of mass term here. So what I know that my moments look like right here is that my moment about the y-axis, this should be m sub y. This is going to be my mass times my distance from the y-axis. And by the way, remember that in general, our moment formula was a summation of m sub I times x sub I or y sub I. Here, we're just looking at one Riemann stick, so there's not a sum. This is just one of the objects. We'll stick the sum on it in our little next block in the notes right down there, right? So in this case here, m sub y should be, well, what's my mass? I just computed it right here. Mass should be rho times delta x times f of x sub I bar. That's my mass. Now, what's my distance from the y-axis? My distance from the y, and now, by the way, this is the sneaky weird part about these formulas. I'm just going to say it right now. Our formulas for these two things are actually not going to be the same, and that's a little bit weird, but the reason is because the way that we make our measurements of where is this point relative to the y-axis versus where is this point relative to the x-axis, they're not really measured the same. One is an input value, an x value, one is an output value, a y value, an f of x value right there. So we're actually going to get not formulas that just replace x and y. We're going to get two different formulas based on how we measure things differently. Our distance from the x-axis of this dot right here, that really should just be that dot's location is x sub I bar. That's just where it's located. It's x sub I bar minus 0, right? So it's x sub I bar. On the other hand, if we did this, our moment about the x-axis, this should be our mass times our distance from the x-axis. In this case right here, oops, I'm writing y again. Our mass, nothing changed right there. Mass doesn't care about the x and y step so much right here. Rho times delta x times f of x sub I bar. But I now have to ask the question, what is the distance that this dot is from the x-axis right here? And we kind of just said this in our diagram that's actually a little bit up above right here. What is the height of this dot? Well, it's half of f of x sub I bar, right? It's half the height of the overall rectangle there. So we're going to get some formulas that are not just swapping the role of x and y right here, right? So this is 1/2 f of x sub I bar. All right. So here's a mass of one Riemann stick, or the moment, excuse me, the moment about the y-axis and the moment about the x-axis of one Riemann stick. Now we need to add up all the moments and then divide by the total mass, and that will give us our center of mass of the entire 2D shape that we're looking at right here. So now when we go ahead and sum the moments of all Riemann sticks, and I'm also going to say, and do the calculus step, let n go to infinity, or let delta x go to 0, right? The calculus component transitioning from the Riemann sum to the integral here. So I'll just say, and let n go to infinity, or delta x go to 0. Then this is saying, let's add them all up, but turn this into the integral form, because we're going to let each of those rectangles get infinitely narrow there, right? So when we do this, then we should be finding that we're just getting our integral from a to b of, right, we're adding up all of the moments right here. So we're going to get a rho. Delta x is getting to be an infinitesimally small dx right there. Also, what's going to happen that's really nice right here is that when our Riemann rectangles get infinitely small, notice that the left edge and the right edge and that middle dot in the middle, they're all converging on one another right there. They're all going to effectively be at the same location once we have n tending off towards infinity right here. So this is just going to be our f of x. And right here, we're just multiplying by a single x. The x sub I bar, remember, it's just like our left and right Riemann sums. Like those are getting infinitely close together. As n goes off to infinity, as delta x goes to 0, those two x values that are the demarcations of the left and right of one rectangle converge on being the same value right here. So this is just going to be times x right there. And so we might then therefore be able to say that my moment sub y, and by the way, I guess these should be like sub I right there because we're only talking about a single one of them right there, something like that. Our overall moment then should be, notice that rho is a constant, dx I want to stick on the end, and so I'm just going to write this now as rho integral from a to b of x times f of x dx. And there now is our integral formula for the moment about to the y-axis. Let's do the exact same thing right here, but again, our formulas are not actually going to look the same because of the way that x measurements just aren't computed the same way as y measurements. One's an x value, one's an f of x value, so we're going to get a little bit different looking formulas here. But similar setup, right? We're going to get our rho, that's just a constant, delta x, or dx, sorry, delta x became dx. We've got an f of x here, and we've got a 1/2 f of x here. So notice we're getting a little bit different of a formula for our moment about the x-axis right here. Rho and 1/2 are both constants, so I'm going to get a rho over 2 sitting out front from a to b, and it looks like we have f of x times f of x dx. So I'm going to get a f of x squared dx, right? So take a moment and look at those two formulas and be like, ooh, we're not just swapping out x information for y information. These formulas actually look quite a bit different. It's definitely the case that I usually have to like look these back up again because I know and I remember enough to be scared that I'm forgetting them wrong, at least typically here. So these are often formulas that when I use them, I've got to say, ooh, hang on, I got to double check my x and y moment formulas here. I know they're a little bit different from one another. So now that we know the moments in general, we can put this all together to find our center of mass formulas for each of them, which is really kind of our big goal right here, right? So to find our x bar, we know that we want this to be the moment about the y-axis divided by the total mass. And so we know that our moment about, I'm going to leave that as moment about the y-axis right now. The point is to get our total mass, just like we did before, mass can be computed as density times area. So we're going to get our rho times area right there. That's our important part. So similarly right here for y bar, we're going to get our moment about the x-axis divided by the total mass. And that's going to be our moment about the x-axis divided by density times area right there. So all we've got to do now is fill this out with the integrals that belong here, and we're good to go. Notice now that this area term is no longer really directly obvious anymore. We were talking area in terms of rectangles before, but now we're not. Now what we're talking about is the area, I guess scroll all the way up to here, the area of this entire region, which you know to very simply just be the integral from a to b of f of x dx. That could be our general integral to get our area of the shape of interest right here. So I will write this a few different ways. This is just one of those things where depending on your scenario, you might want to use one version versus another version here for our formula because sometimes our areas might be geometrically computable. Other times we might need to actually do the integration to find the area of our region of interest here. So I'm seeing here that my center of mass about the y-axis was rho, integral from a to b, x f of x dx. And it looks like we're dividing this whole thing by rho times a. And so it looks like these rows are going to cancel from one another. It looks like our center of mass is independent of density as long as density is constant. You should absolutely be thinking to yourself that there's plenty of things where the density of the thing is not consistent throughout the object. In that case, density would be its own function of perhaps of x and y. And again, something you're going to look into in Calc 3 once you're able to handle a few more variables out there. So it looks like we could kind of state this as 1 over a times the integral from a to b of x f of x dx. And alternatively, this is the way that I would do the computation if the object was geometric and I could just compute a without calculus. If I need to compute a with calculus, then the area is just going to be the integral. Let's say the area underneath the function f of x, right? So I think I could write this then as something like integral from a to b of x f of x dx divided by the integral from a to b of just f of x dx, right? Just the area underneath the curve right there. So that would be our x bar center of mass there. Very, very similarly down here for the y bar center of mass, it looks like we're getting rho over 2 integral from a to b of f of x squared dx, all divided by rho a. Those are going to cancel. Dividing by 2, I can put that in the denominator right there. So we're going to get 1 over 2a integral from a to b of f of x squared dx. Again, this is a good formula to use if the area of our region of interest is geometric and we can compute it without calculus. If we need to use calculus, then we should be getting something instead that's looking like a to b of our f of x squared dx divided by 2 times the integral of the area. All right, so there we go. We built the formulas of interest for ourselves here. I would say that this is kind of might as well just write my equals x bar and equals y bar right here and box the whole dang thing. And these are the formulas that we can now use to find the center of mass in terms of an x bar, y bar location center of mass of any irregular object as long as we have a function defining its boundary. So let's go ahead and do one here. We're going to do one problem, and you're even going to see a bunch of the parts are going to fall out, but you're going to see all the steps that you need to be able to see in this problem. So given that the object is a density of rho equals 5, this is 5 kilograms per square meter or something like that. Let's find the center of mass of this object right here. And so here's what I'm noticing. As I suggested up above, in a lot of cases here, these center of mass problems involve what I would kind of refer to as sort of like a piecewise defined region. This region is very awkward if you try to think of it as one region. This region is really simple to think about as long as you think of the top half, the top part being a semicircle and the bottom part just being a square. So here's what our strategy is going to be broadly overall for this thing. Let's find the center of mass of the square and its mass. Let's find the center of mass of the semicircle and its mass, and then use those two as sort of like point masses to then do our two-dimensional problem like we did as our second example. We'll kind of join the two solutions together right there. So here's kind of what I'm thinking to myself. I'm thinking to myself that this sort of represents the top piece of my object, and this is my bottom piece right here. And what do we have going on for our top piece? Well, we know that our equation of a circle is x squared plus y squared equals 1, which we know that we can very easily solve as y equals the square root of 1 minus x squared. As it has happened 1,000 times this semester, technically speaking, this gets a plus or minus right here, but we're only interested in the top half, so we're only keeping the positive part right here. It looks like in this case, x is defined over the boundary from -1 to 1. And right away, before I even go on right here, I want to ask you, like, what do you think we're going to get for the center of mass and the x component of the center of mass and the y component of the center of mass? What are we going to get for the x component of the center of mass of that semicircle? Since it is equally distributed on left and right, since we have perfect left-right symmetry with this thing, by symmetry, I think it's very easy for me to make the statement that the center of mass of the top part of this object is clearly going to be located at 0, right? There's just no way with the semicircle the center of mass would be shifted to one side or the other since this thing has equal density everywhere right there, right? Now, where is our center of mass in the y department going to be here for that top object? That's not clear to me yet, right? But I know by symmetry that like left-right symmetry, it's obviously going to be in the middle because we have left-right symmetry. Very similarly for the bottom function right here, you should notice that this bottom function is defined by the function y equals -2, right? There's the line that I'm thinking. There's y equals -2 right there. And it looks like this is defined over the x interval also from -1 to 1. And now again, my question to you is, do we know either of these? Well, where's going to be the center of mass, the x coordinate of the center of mass of that bottom square? Because it's a square, hopefully we're all down with the fact that these simple geometric shapes are going to allow us to just make some symmetry claims and say, I know exactly where that is, right? There's no mystery to me on that one. Because this square has perfect left-right symmetry, it's got to be at the middle, right? So it's got to basically, it has to just be sitting right there. We also have top-bottom symmetry, right? I think I know just by symmetries alone that the center of mass, the x-coordinate of the center of mass is 0. And we also, I think, know the y-coordinate of the center of mass for this bottom object right here. it's got to be at -1, right? It's got to be halfway between the top and bottom because these are such nice symmetric objects right here. So you should notice I'm picking out, in a sense, a kind of nice problem to do. This is still going to require some work for us right here. But the point is, we just need to do some work to find y bar top, and we have all the information that we need to then finally compute our final answer, right? So there's still going to be a step after that because these are just the center of masses of the top object and the bottom object individually. Then we'll need to combine those results to get the overall center of mass of the overall object. But what I'm thinking is, I'm kind of guessing, like, the point is here, I don't know where on this y-axis our center of mass is going to be for this top object right here, but it's got to be something like this, right? And this one's going to be somewhere here. So the point is that we think that this is going to be like our guess then would be that we're going to get something like this as our overall answer right there. Right? That's kind of my guess, is this location right there somewhere that we're going to find the center of mass of the overall object here. So we just need to do the work to find y bar top, then combine the top and bottom info. So notice the strategy here. Strategy is really important. Calculus is just taking more integrals that you've already taken before. We're not going to take a hard integral today. The strategy is what's really important here. We're looking at this as two shapes individually that we can easily discuss. Then after we found the center of masses of the individual objects that we've decomposed the overall object into, we then think of those as point masses located at their center of mass and find the overall center of mass between each of the groups of objects. So there could be, maybe this square actually had, oh, okay, if it had semicircles on all four, then it would definitely just be in the dead center. But the point is, right, we could have had a triangle on this side and another square on this side and a long rectangle on the bottom and a square in the middle, semicircle on top. I would have instead just found the x bar, y bar for each of my 5 individual shapes and then found the overall center of mass from their center of masses and the mass, right? So a lot of these end up being sort of these like piecewise problems right here, and that's exactly what we're doing with the strategy right here. So it looks like we need to find a y bar is what we need to be able to find right here. So let's find y bar top, and I'm going to just scroll up and see. I'm going to remind myself, what was my y bar formula? We decided that our y bar formula, now again, we've kind of got these two different formulations of it right here. I don't think I need to use this one with the two integrals on the right because it's really easy for me to talk about the area, in fact, of both of these objects. The semicircle, I can talk area geometrically. Square, I can talk area geometrically. So I think I'm going to use the formula with the a in it right here. So 1 over 2a times the integral of f of x squared from a to b. So 1 over 2a, integral from -1 to 1 of f of x squared dx. All right, this is my formula I'm using right here. So I need to know two things. One, what's f of x? B, what's a? Well, we just said this a second ago. Scrolling back up right here. Scroll a little too far. We're looking at the y bar of the top is like our one unknown right there, right? So our formula for f of x is just the square root of 1 minus x squared. We also need to know the area of the top. The area of the top is half of the area of a unit 1 circle, or a radius 1 circle. So it's half of pi times 1 squared. And that looks like it's just going to be pi over 2 is the area of that semicircle right there. So we've got all the information we need. The integral is going to be really easy. Let's do the dang thing. So 1 over 2 times the area, integral from -1 to 1 of, oh, look at how nice this is. By the way, this looks like this was the integral of an even function, so we probably could have just, over symmetric bounds, I think I could have doubled it and gone from 0 to 1, but I wasn't paying attention. I've already written too much, so we're sticking with it. It's an easy one, though. So what? 1 minus 1/3 minus -1 plus 1/3. Okay. And it looks like that's giving me 2/3 minus negative 2/3. So 2/3 plus 2/3 is 4/3. 1 over pi times 4 over 3 equals 4 over 3 pi. So it looks like that is our y bar for our top. So we've now found what that center of mass location is just of that top semicircle, right? But we already knew all three of the other components that we actually needed right here. So we're actually in really good shape. So what have we got so far? So using this as our y bar result right here. This is our y bar of the top of the two pieces right there. And so let's kind of conclude where we're at so far. The center of mass of the top, its xy location, was 0 because of left-right symmetry, and 4 over 3 pi based on the calculation that we just did. Our bottom shape was really easy because it was a square, so we just got to claim the whole thing by symmetry. That is just the middle of the square. And that left us at 0, -1. Right? So now to get the center of mass, what do we still need? Let's scroll up and see. To get the overall center of mass, to get our overall center of mass right here, we still need to find, oh sorry, I didn't scroll up far enough right here. Now to get our overall center of mass, we want to combine these two right here, right? So now we're going to say, listen, I've got the mass of two objects. I've got the locations of those two objects, thinking of them now as point masses because I've found where their center of mass is. And I can now find this sort of like this weighted average that will give me the actual center of mass of the overall object rather than of the individual objects themselves. So a good thing to do with this example is to picture for yourself that A, B, and C, we're kind of thinking of these now as actual center of masses of like other objects that are out there, right? This is defining some weird object center of mass, 3 of them maybe. We've considered it as a point mass because we found those weird shaped object center of mass. Then we can group up the center of masses to find the overall center of mass between several objects. So let's go ahead and do that here. Oh, sorry, I'm scrolling away. Well, notice that the thing that we still need here is that we have found the information that is we have the area, we have the density, we need to get the sum of each of the two masses times their x and y locations divided by the total overall mass right here. So let's go ahead and do this thing here. So we'll draw the rest of it in our final diagram down here. To get overall center of mass, still need the mass of the top and bottom. We found the area of top and bottom, not the mass. The mass of the top is going to be the density of the top times the area of the top. Density was given as 5. We already found the area of the top piece. That was the semicircle with area of pi halves. So we're getting 5 pi halves is the mass of that top semicircle. The mass of the bottom square is the density of the bottom square times the area of the bottom square. Well, the density of the bottom square was 5. What's the area of the bottom square? You saw 1s out there earlier, but realize it goes from -1 to +1, so this is actually a side length of 2. So our area of our overall square is 4. And that gives me 20 for that mass right there. So we can say we know x bar overall equals 0 by symmetry. And we compute the y bar here as the sum of the mass times the y location divided by the sum of the masses. And so what are we going to get right here? The mass of the top object was 5 pi halves. The y location of the center of mass of the top object was 4 over 3 pi. We're adding to this the mass of the bottom object, which is 20. Notice a lot more mass with this bottom object here. That square's a lot bigger, so its pull is going to be a lot greater for where the center of mass is going to be located. Times the y value of the center of mass of the bottom object, which we determined to be -1, right? We got that right there. The y value of the bottom center of mass, is -1. That's pulling it down. And this is divided by the total mass of the entire thing, which would just be the sum of our two masses. 5 pi halves plus 20. And if we do a little simplifying here, I can see some things like pi cancels with pi, 2 cancels with 4 to give me a 2. So this looks like I'm going to get 10 over 3, minus 20. All divided by 5 pi halves plus 20. And once again, I already went through this in my calculator here a moment ago, and I arrived at the estimated value here of -0.59836 as my y bar estimate to 5 decimal places right there. So what we've found overall here then was, I'm going to drag this guy down a little bit. This was our location. Oh man, I don't know why I'm not allowed to draw on these. That one worked. Come on, man. Yeah, that worked. That's weird. So this was our top center of mass. This right here exactly was our bottom center of mass. And once we found the individual center of masses of the top shape and the bottom shape, we were then able to use our discrete formula, thinking of those as just two point masses rather than two surfaces, to find the center of mass of those two discrete points in space right there. So then we ended up finding, so if this is at -1, then here, right about, here is going to be our negative like 0.6, right? So this is our overall center of mass. That we just found. So I think we can conclude here that x bar, y bar was located at 0, -0.59836 right there. All right, so there we go. So today's one of those funky days where, and I mean, I'm being honest, this is definitely not one of my most comfortable teaching days right here. This is certainly a physics engineering heavy concept day right here. But overall, I really, really like the geometry that's associated with these. When you guys kind of see some of the problems that are associated with these, I think people kind of typically like these. These are kind of cool, little puzzles of putting together lots of different geometric shapes and finding the center of mass of the overall shape. And so the big takeaway for this is that we have a strategy here, which is you're very rarely going to do one of these problems and just find the center of mass. This is very often something that's more like find several individual center of masses, either using our continuous or our discrete formulas, then sort of assemble your overall center of mass using our discrete formula right here, like we did at the very end, where we add up the mass and we computed the moment of the 2 point masses for the top and bottom. If we interpret this square as having all of its mass just at that point, this semicircle is having all of its mass just at that point, then we can think of these as 2 discrete point masses over which we can find the overall center of mass right there, which we did in this example right here. So the other thing, just to kind of warn you about, remember that these formulas are they're kind of weird in the fact that they're not the same as each other. I mean, we get x times, and I guess they kind of are. There's x times f of x versus f of x times f of x, but then the 1/2 is a little bit of a weird one. When I derive this formula, every time I'm like, oh yeah, this makes total sense, but later when I look back at the formula, I'm like, wait, where'd the 1/2 come from? Why are these different integrands right here? So I would encourage you to kind of I don't know, go back and reread through this derivation of our formula right here, because it's one of those ones that really does make sense. But when I don't know, you go to look at this formula a year from now and you're going to be like, I don't remember why those were like that. And that's not an uncommon experience right there. So just be aware that you might have to be referencing these formulas a little bit right here to make sure that you don't get them backwards or anything like that. Recognize that today our 2 A terms were easily found geometrically, but if you're looking for the center of mass of some region that's defined as the area between 2 curves, then you're probably going to need to be doing some integration down there. And in fact, that integration is going to be the integral of like an f of x minus a g of x if it was the area between two curves, stuff like that. So recognize that this is more of a generic way to say area, but it might often be the case that you're going to like integrate from a to b in f of x, or a difference of f of x and g of x if it's an area between two curves right there. So there we go. So there's our one example. Even though 3 out of the 4 parts that we needed were just kind of automatically given to us by symmetry, there's still some work involved to find one of our parts' center of masses and then combine our two results into an overall center of mass right here. So that's going to wrap it up for me for section 8.3. I'm going to see you guys in section 8.5 in the next video. Probability is one of those things where, man, if I got to just pick any class I ever wanted to teach, aside from how much I enjoyed teaching programming classes, if it wasn't allowed to be just a programming class, then next on my list would be a calculus-based probability course. I want to teach an entire semester of calculus-based probability. Unfortunately, we're going to get only about an hour's worth of stuff, but what I'm going to convince you in the next class is that every value, pretty much every value in probability and statistics that we compute of interest, okay, that's a bit of an exaggeration, but a vast majority of all interesting values computed in probability and statistics are all calculus defined. It's why I have such a hard time teaching intro to probability and statistics, intro to stats at CR, is because every single computation that we do, somebody's asked me the question, hey, where does that formula come from? I'm like, take 2 semesters of calculus and I can tell you. And it's so disappointing because it's very rare that my students have ever had the calculus in that class. So I love teaching probability when I get to know that you guys know some calculus beforehand. So what I'm going to show you guys in the next video is that things like mean, median, mode, standard deviation, all of these things depend on calculus to actually define them, which is just something that we have to miss on every person's intro to stats class, which drives me insane. So you guys finally get the good look at it. The thing I'm going to convince you, I'm going to yell at you about it right now as my closing statement. I'm going to yell at you about it 5 times during the next video. If you guys have already taken Math 15, Intro to Statistics at CR, most math people usually don't like that class. When I took Intro to Stats when I was an undergrad, I thought it was one of the lamest math classes I'd ever taken, because I was like a junior taking this Intro to Stats class. Then my very last class that I took as an undergraduate student was calculus-based probability, and I would say that it was easily in my like top 3 classes I took in all of undergrad. It was so fascinating. Really cool stuff. So now that you guys know calculus, my big pitch to you guys is you've got to go take an upper level probability class at some point, a 300 or 400 level probability class. It's crazy interesting. It's just so heavy dependent on calculus that you can't talk about it without several semesters of calculus. And so we got to get that probability and statistics intertwined with what we otherwise think of as more of like the engineering fields out there with the calculus stuff. So really good stuff. Looking forward to 8.5. I'll see you guys in the next video. Have a good one.